Last time, we looked at these two equations as a way to determine if there was any energy at a particular frequency f in a mystery waveform, which, as an example, might be my voice. And the way we looked at it was we could test different frequencies f and just see if there's any energy at that frequency. What we want to look at today is how to do this in a computer in an efficient way so that we don't just simply check one or two or a few frequencies, but we're going to check all of them at one time. And this equation over here is really a continuous equation. And just as a reminder for those of you who don't know what the squiggle is, which is integration, just think of it something like averaging out the value made up by whatever these two things multiplied together produce. Anyway, if we want to do this using a sampled signal, as when we deal with stuff in a computer, we have to consider a few things. And the first thing is, how often do we sample it? Well, usually on a CD, you get a sampling rate of about 44 kilohertz or kilosamples per second. And the reason that was chosen is half of that is 22 kilosamples per second, or in the case of audio, 22 kilohertz. And it turns out for every hertz of bandwidth you need twice as many samples per second. So in theory, this could handle audio up to 22 kilohertz, but in reality, there's probably a bit of leeway in most systems, so most audio systems go up to perhaps 20 kilohertz on a good day. Some of the newer systems, including the system that I'm recording my voice with, use a slightly higher frequency, 48 kilohertz. In the end, it doesn't really make that much of a difference, other than it is an indicator of how many points we're going to have to deal with. So if we have 1 second of audio and we're using 48 kilohertz sampling, or 48,000 samples per second, that means in 1 second we're going to deal with 48,000 points of data, of audio. That's a lot of data to deal with. Now, what that does mean is if we're going to deal with 48,000 points, it means we're going to use 48,000 times this equation. In other words, we're going to have it at t equals 0 and t equals 1 and t equals 2, all the way up to t equals 48,000, where 48,000 is the last point in that 1 second of time. Now, it also turns out that if we have n points, or n audio samples in time, we want to end up with n frequency bins, or values of f. And what that means is, if we have n points and n frequency bins, we have to do this calculation n times n times, or n squared times. That's a lot of computation. It's really a lot when you're dealing with a large number of n. Even a smaller number of n, like 1,000, would, for instance, produce an n squared of 1,000,000. And if you remember anything about trigonometry, it's actually quite hard to do these calculations, so you'd want to minimize it. And that's, in fact, the whole idea behind what's known as the fast Fourier transform, the FFT, and it can actually minimize the number of calculations to being a lot less than n squared. Before we do that, just in preparation of moving towards thinking about the FFT, I want to show you two other things. We were dealing with an x value and a y value, and I'd sort of hinted that these correspond to real and imaginary parts of a complex number. So we're really going to start calling this the r value and this the I value, but it doesn't really change anything in here. The other thing that's worth pointing out is last time I showed you how you could plot the value of x and y on a graph and look at the radius here using the Pythagorean theorem and get the length of the radius so that you could in fact see the absolute value of the sinusoidal wave, even if it wasn't exactly a cos wave or a sine wave, but at some angle between them. And I also said we could use the inverse tangent function to get the angle. And if you didn't already know it, most computer math packages in most languages have an arctan function that actually gets y and x as the input parameters and produces that value of angle right there for you to make it really easy. So with all of that said, I want to give you a rough idea how the fast Fourier transform over here can get around this problem of having to do n frequencies and n samples. In other words, do n squared calculations and make that into something much less computationally intensive. So I took this printout from the Wikipedia page on FFTs, and what it does is shows the fundamental way FFTs reduce the amount of computation needed. And the way it does that is it actually takes an FFT, in this case they've shown one using 8 input samples of data, which would normally be 8 times 8 computations. And it turns out you can actually split it and do 2 half-size FFTs, which only have half as many points to deal with. And by the way, you'll see it says DFT here for discrete Fourier transform. FFT, fast Fourier transform, is just a fast way of doing the discrete Fourier transform. So for our purposes, they mean the same thing. Well, for n points, we have n squared calculations. For n over 2 points, we have n over 2 squared calculations equals n squared over 4. And if we take the other half of the points, and you'll notice they're separated into the even points and the odd points of our time sample data, we can do another half-size fast Fourier transform calculation, which again consumes n squared over 4. Or put that all together, and magically what we end up with in the total is simply n squared over 2 calculations. Half as many calculations as the full n squared we needed if we did it as one giant fast Fourier transform. So the bottom line is we can deal with the data in 2 sets of 1/2. Now, you do see this sort of crisscross mishmash over here, and what that is showing us how we have to combine these 2 sets of data so that we ended up with 8 output frequency bins corresponding to the 8 input time samples. And what it's saying is we're going to get the output from this first FFT, and maybe I'll use another pen just to show you better. As an example, we'll take the output of the first FFT, and we're going to take the output of the second FFT, and it's the first entry in each of the outputs. We'll multiply the second FFT's output by some weighting factor and then add it to the output of the first FFT, and that will give us the output of the combined FFT. And then we repeat it again and again and again in each one of these crisscross directions. And I was sort of looking at this, and somewhere we're using perhaps n or n2n perhaps calculations, something like that, to achieve this. So what you could sort of argue is that for the combined now 2 times half size thing, we end up with n squared over 2 plus 2n or something like that. You'd really need a more detailed analysis to know for sure. And in fact, it turns out that if you now repeat this process and take these 2 half-size FFTs each and split each of them up into half-size FFTs and work on them the same way, and then take those smaller ones and split them up and keep repeating it till you have essentially one data point left, you end up with a massive saving in computation. And the saving is in fact n log n. So it's not n squared, it's n log n calculations. And log n is really a very slowly growing function. And to show you how effective that is, I've printed out some graphs, and here they are. Here's a graph that's showing n squared up here, and it's a parabola, and it's just shooting up in the distance. And well, maybe we should just mark it here. This is n squared, and this is n, the number of samples, and you can see that even at, well, somewhere around 300 samples, we're well into the hundreds of thousands of calculations over there. Now, if we look at n log n, it's this line over here. You can see that it's almost not going up at all compared to this other one. Yes, it's increasing, but just very gradually. In fact, it almost looks like a straight line. It isn't, but it sure looks like it on this scale. And just to give you a sense of how effective that is, we can even just switch sheets of graph paper one more time. Look at it on a slightly larger scale of n, where n is now going up to 10,000. Well, and when that happens, n squared almost goes straight up, and our good old n log n, well, you can see that it's just slightly curved, but it's basically just rising at a nice even pace. And well, you can sort of see that over here at about 10,000 points, we have less than 100,000 calculations to do, which on a modern computer is not a big thing. I also drew one more line, and this line over here is simply n. So that's n, and this is n log n. And this is n squared. Well, n would be ideal because it would just mean for every point we do one more calculation. Well, that would be too good to be true. But even at that n log n is still pretty good. And of course, n squared is crazy. So for virtually all applications, the fast Fourier transform is in fact the way to go, because you can do larger and larger data sets with only gradually increasing amounts of data. There are a few exceptions, and that is if you only had a few points on your whole data set that actually had a value and were zero elsewhere, then you might find that some sort of a brute force method is better, and I know that's done with astronomical signal processing. But other than that, the fast Fourier transform rules. The next thing we should look at is how FFTs typically work in computer libraries. And the way they work is, more often than not, you have some sort of a computer function called FFT, surprisingly, and it takes an input array of the sample points, and it gives you an output array of the frequency bins, and it also usually has some sort of a Boolean called inverse or similar, which tells the fast Fourier transform algorithm whether you're going from a set of time samples to a set of frequency bins, or whether you're going in the other direction, because it turns out you can just as easily go from a set of frequency bins back to a set of time samples, which is very convenient for signal processing. Now, the input and output arrays are generally a bit different than what you might at first expect, and that is, depending on the computer language, each of the sample points on the input or the bins on the output has two values corresponding to the x and y values that we'd previously talked about, although we never mentioned them for the inputs. And in this context, they're actually considered real and imaginary parts. Again, it's just a different name. So the input array would be declared probably something like this: input with n points. And so it would have a whole bunch of entries in the array. Entry 0, entry 1, entry 2, on and on and on, up to entry n. And each one of these entries has a real part and an imaginary part. And on many languages, you would write entry 0 like this, where 0 is the 0th entry, R is the R part of it, and we would say equals, in our case, m of t0, the first time sample. And now you might say, but what do we do with the imaginary part? Well, we're going to say input of 0 dot imaginary equals 0. And then we would continue that on, input of 1 dot r equals the input signal at time 1, and the imaginary part of that will be 0, and we would just continue it all the way down to the nth sample point. Don't worry about these imaginary parts being set to 0 right now. We'll cover that in some future video. For now, it is simply the same thing as in the equations that we had looked at before. We're going to be multiplying the cosine and sine functions by these values over here. So that's the input. We should now look at what we're going to get at the output side of the transform. So how do we deal with the output of our FFT? Well, the output is an array of size n, and that is n frequency bins. And each one of the array entries has a real and imaginary part. The 0 with 1, for instance, would have a real value, which is some value. And it would also have an imaginary value, which is some other value. Might be the same, out of pure random chance. And I should point out that different computer languages might represent this slightly differently. One way or the other, it amounts to the same thing. There are real and imaginary parts, and they correspond to our old x value from the cosine and y value from the sine calculation. And the question really is what frequencies do each of these bins correspond to? So let's just draw a nice little diagram and see if we can figure that out. So what I'll do here is draw a diagram where this axis going up here is the amplitude, and each entry here is a bin. So this would be the 0 bin, this would be the 1 bin, this would be the 2 bin, all the way up to here, which would be the n-1 bin, because there are n points. So the maximum one here is n-1 if the first one is 0. And in the middle, not surprisingly, there is a bin corresponding to n over 2. And it turns out that this bin here corresponds to the sample frequency that we use to sample our data. In other words, the number of samples per second, 44 kilohertz in the case of many audio streams, or 48 kilohertz, but it's that sample frequency over 2. That sort of makes sense when you think about it. You would expect at the halfway point to be halfway through all the frequencies. But remember I said that if you're sampling at a certain frequency, like 44 kilohertz, the maximum audio frequency you can faithfully sample and reproduce is half that? Well, that means that this frequency here, f over 2, is the maximum frequency we could ever hope to have properly sampled in our data. So what that tells us is that these frequencies over here can't possibly be valid. Well, you're right. They can't be valid in terms of being greater than f over 2. The trick is they're not greater than f over 2. And it turns out that if these bins, we'll call them frequencies 0 and 1 and 2 and so forth up to n over 2, over here we have n-1 corresponding to a frequency of -1, and then the next bin corresponding to a frequency of -2 and -3 and -4, all the way up to here. So oddly enough, we end up with positive frequencies here, and we end up with negative frequencies here. And we could say, what on earth is a negative frequency? Well, if you think of our original formulas, which looked something like cos 2 pi FT, all of that times m of t, the mystery waveform, and all of that integrated, well, the negative frequency corresponds to this f over here being negative, whatever that might mean. And we will worry about interpreting that in a future video. But if we go back to this here, what we really want to do is figure out what frequencies each one of these bins or positions in the array correspond to in terms of actual frequencies. And to do that, let's redraw this on a separate sheet of paper and continue there. Okay, so I've redrawn our graph a little bit, and I sort of made the distinction that we have the array bin position corresponding to the index of the array, 0, 1, 2, 3, n over 2, and then n minus 4, minus 3, minus 2, and n minus 1 to the final position in the array. But I've also, below that, to make it a little bit clearer, written in, here are the frequencies of those bins. 0, 1, 2, 3, and then the negative frequencies over here. But these are sort of unitless frequency bin numbers. And again, what we really would like to do is know what each of these bins corresponds to in terms of a real frequency. And we can do that quite easily because we know this middle bin, as we said before, corresponds to the original sampling frequency over 2. So if there are n over 2 bins over here, with the first bin at 0 frequency and the n over 2th bin at f over 2, it's actually quite easy. And that is, each bin is f over n hertz. That's all there is to it. So we can now actually assign real frequencies to these numbers. And it also tells us something really neat about how close together these frequencies are. If we make f really big, the differences in frequency between these bins gets larger. If we make n really big, we use a lot of samples, the distance in frequency between each of these bins gets smaller. So we can choose our sampling frequency and number of samples to determine how many samples we have and how wide each of these frequency bins are. And we would choose that based on what level of detail we want in determining the spectrum. So that's really all there is to it in terms of figuring out frequencies. Now, it's sort of unsettling to have 0 going up to some big positive number meeting up against -1 going up to some big negative number and sort of meeting in the middle. It would be, in fact, much nicer if our frequency graph actually was like this. And maybe we should even just get rid of this over here, put an axis in the middle over here, set that to 0, and what we're going to do is we will move these things over here. So we have our 1, 2, 3, all the way up bins in this side, and we will take these values and shove them over here. So we have our -1, -2, -3, and so forth values over there. Where again, this is now frequency. And many FFT algorithms have some sort of a function called something like shift, which in fact does this shifting so that we now get our zero frequency in the middle, our minuses on the left, and our positives on the right. And you might ask, well, if we have this function to do it, why doesn't the FFT do that in the first place? Well, it turns out the reason for this weird ordering of outputs has to do with the most efficient implementation of the FFT, and in most cases this is just where the data falls, and it's generally left like that because often you can use it like this without going to the extra effort of shifting it around something like this. So that can be your choice as to what to do. Again, for our purposes right now, if we're just looking at spectrums of simple functions like m of t, voice, for instance, all we're really interested in is this part of the data anyway. And just like with the x and y's, we can get an amplitude and an angle or a power for each one of these bins and draw some sort of a pretty spectral graph if we so choose. So that's really all there is to it in terms of using most FFTs. The main thing is you end up with these funny negative frequencies, which might seem disconcerting. And as I said, we'll talk about it in the future. And you also end up with this sort of strange spectrum where you have a discontinuity between the positive and the negative numbers that you might want to swap to make them at least follow in a normal numeric sense from low to high. There are a number of FFT libraries out there. The one that I use as sort of a go-to library is the KISS FFT, and KISS stands for Keep It Simple Stupid. And that really was the philosophy of the fellow who wrote the library. He was looking for a library and apparently couldn't find one that he was happy with, and so he wrote this one, and it's not necessarily the fastest, but it is widely available. The nice thing is it is open source, and it has a very liberal license. And what I mean by that is you can use it for pretty much anything you want. Some of the licenses out there for other libraries are restrictive. You can't use it for commercial stuff, or if you do use it for anything, you then have to open source your code to the same terms as the license of the FFT package. Well, KISS has none of that. It's basically you can use it and do anything you want with it, and I don't know if it even requires that you acknowledge them or not, but it certainly would be a good thing to do. This is natively written in C, and that's actually a pretty good thing because C gets compiled down to native machine code. In other words, to the instructions that the particular processor in your cell phone or laptop or whatever executes right in memory. And that's kind of important because machine code is very efficient. Not all languages get compiled to native machine code. In fact, most notably, languages like Java get compiled to an intermediary type code, which then a runtime environment on the fly, if you want, translates to machine code. and JavaScript is actually interpreted on the fly. Neither approach is anywhere near as efficient as something like C being compiled right down to native machine code. Now, it all depends on what you're doing as to whether that's important or not. If you're only handling a few hundred points and doing it once to get a spectrum, in fact, the FFT written directly in each of these two languages will work, and people, I believe, have ported KISS to both those languages directly. However, if you're doing something where you need to handle thousands of FFTs very quickly, and each one has thousands of sample points, well, running things in the Java virtual machine or the JavaScript interpreter really won't do it. I know people have created Java native interfaces so that you can call the KISS FFT compiled C code directly from Java. I could be wrong, but I don't think that exists for JavaScript. The bottom line is, depending on what you're doing, you need to look out for how the FFT library is implemented for your particular language, and there may be some options. And this applies for all sorts of other languages as well, be it high-level languages like PHP as another example, or legacy languages like Fortran, or really you could even include things like MATLAB and the open source equivalent Octave, both of which in one way or another end up calling native machine code. But in general are rather easy to use but slow languages. So the bottom line is, I highly recommend KISS FFT. I've used it. There are other FFTs out there. They're all quite similar in one way or the other, some slightly better, some slightly worse. Whenever you're using a software library, consider what the license terms of that library are, and in particular whether it would require you to open source your code, which you may not wish to do depending on the application. And you also need to look at how the library is implemented in the particular language you happen to be using, and if in fact it's going to be fast enough for your application if you're doing vast amounts of processing. So that pretty much brings this video to an end. Next video on FFTs will actually be a more general discussion about Fourier transforms and negative frequencies, and what about those imaginary numbers on the input data, which we just set to 0. See you then.